Hello and welcome. I'm Hak from Akasa. For those who are not familiar, Akasa is a healthcare tech startup uh, that automates healthcare operations with AI and currently serves almost 15% of US healthcare systems. In this presentation, we'll discuss how well current explainability methods help advanced neural networks predict correct medical code and provide references and clinical notes supporting the code prediction. Let's start with the patient's hospital visit and a particular inpatient scenario in the hospital. An inpatient scenario can be highly complex as it often includes several medical research and notes from various doctors seen during the patient's hospital stays. As an example, meet Sarah, a patient with diabetes. Sarah is admitted by her primary doctor. She gets checked and receives the necessary treatment during her hospital stay. After a few days at the hospital, she goes through the discharge procedure and receives a discharge summary. Finally, she goes to her local pharmacy to refill an insulin prescription after discharge. For that, Sarah's medical record and chart, her treatment plan and discharge summary, for example, need to be converted into a specific healthcare document using a standard format of medical code. This ensures all healthcare providers involved are getting paid correctly for their services from Sarah's insurance, or partly herself. This is where medical coders come into play. Their job is essentially to translate the specific healthcare diagnosis, procedures, and medical services that have been provided to the patient into universal medical alphanumeric code that are required by insurance companies. So then, what exactly is the medical coding problem? Well, Sarah's clicker notes contain a lot of information about what precisely happened during her entire stay. Here you can see an example of a discharge summary, which is typically long, loosely structured, consists of medical domain language and sometimes written with spelling errors. The medical coding problem is now to annotate this written clicker note from the doctor with the correct medical code the insurance companies need. Note that there are nearly 70,000 total codes in the current ICD-10 system, which means International Classification of Diseases. So this is a highly complex and multi-labeled classification problem. That is why, unlike prior works, we approached this problem as an assignment learning problem from the set of input sentences to the group of code and developed an ICD system agnostic model. When you closely look at this problem, it becomes clear that developing algorithms that automatically read, interpret, and assign code individually could be a very high value for these coders who currently do this work manually. To tackle this problem, we introduced the read, append, and code RAG algorithms last year that can read, interpret, and assign code automatically by predicting proper code from clicker notes. The reader is the most recent transformer encoder combined with CNN layers. The coder helps the model focus on the important part that matter for each code and assign each code individually. After developing these new RAG algorithms, we benchmark our model with a publicly available mimic data set. We were particularly excited that the model wins over all the previously reported state-of-the-art methods across various standard metrics. Papers with code even created a leaderboard in the medical code prediction test, ranking our approach as number one and the state-of-the-art. And we even found that our model reached past human level baseline measured internally. But this is not the end of the story. To gain trust for this automation system from professional medical coders, the system needs to provide some level of explainability altogether with predictive code. In particular, the research question that we intended to answer was, how can we generate evidentiary text snippets for predictive code to provide textual references and explanations of those codes? This is how the extract framework was developed, which allows us to obtain supporting text from clinical notes that justify the predicted medical code from the code prediction system. Out of two approaches that we looked at, the first extract attention approach is to use the attention scores computed from the attention module in the coder, which are denoted by W scores here. The second extract knowledge distillation KD approach is to transfer the large RAG-based teacher model into a set of linear student models by distilling the large teacher model's prediction. Finally, the evidence text of both extract attention and extract KD models is constructed in the following way. First, for each code, finding the n-gram with the highest average weight score. Second, including M tokens on either side of the n-gram to obtain the final subsequence of evidence with length n plus 2 times m. Here are a few constructed examples. Additionally, due to the nature of medical coding, frequent code associated with common diseases will receive more updates than infrequent code during the training phase of the RAG model, and similar for input tokens. In other words, the trained model with binary cross-entropy loss, BCE loss, tends to focus more the frequent code and their associated clinical node portions in the dataset. Therefore, we propose two losses to augment the BCE loss in order to encourage the model to better handle the previously described imbalance issues and improve the model's overall performance. Here are some performance results. First of all, the extract attention model improved both standard and hierarchical micro-F1 scores over the RAG baseline, suggesting that the augmented prior matching losses might still help. Secondly, the extract KD student model is performing slightly worse than the RAG-based teacher model. However, it still shows significantly better result than the logistic regression baseline across the board, which has the same level of model complexity. To evaluate the extract framework, we conducted a human evaluation in a simplified scenario with two groups of annotators. Group A consists of two annotators with a medical coding experience, and Group B includes 6 certified professional coders. Both groups are given a total of about 3,800 predicted code with supporting text snippets and are asked to assign one of 3 choices to each: highly informative, and irrelevant. For both groups, the ratio of informative text snippet to the total extracted snippets showed that extract attention is a more viable choice than extract KD for extracting a text snippet from clinical note to support code prediction. Furthermore, the fact that the consistency score between the two groups is less than 40% even with extract attention suggests that the automated extraction still requires feedback from professional coders. In other words, there is still room for improvement for current explainability so that even a non-coder can handle this task well. In summary, despite the fact that the machine's prediction accuracy was shown to be higher than human coders in the previous RAG paper, for the first time, we showed that given the current state of explainability methodologies, using the proposed explainable yet accurate medical code prediction system extract still requires professional coders' expertise and competencies. Finally, the deep learning-based prediction models' limitations still remain relevant because human coders occasionally combine disparate pieces of patient information together. For example, updated coding guidelines. For more information on this project, please visit my personal website here. And to learn more about Akasa and other research we're doing, you can visit our website and check out the latest in our blog. Thank you for your attention and joining me today.